Haven't you always wanted to see the inside of an airplane engine? Me too. That pay attention, and in this rest of 7.3 we're going to talk about osmosis. We're going to talk about solutions. If you see in 13 that are hypo, hyper, and isotonic to cell contents or the environment, there's 14 is about osmosis, and then we'll look at some biological examples for objective 15. The definition of osmosis. It's the same thing as the definition of diffusion, but it's the diffusion of water. So you have to imagine it's the diffusion of water across a selectively permeable membrane. Now, I told you that most environments inside and outside of cells are water-based. We live in an aqueous medium. All of our cells do. Why would water ever want to move from one side of a cell membrane to another? And what would cause it to move? This is osmosis. It's the movement of water. Again, this is a passive process. No energy is being used in this process. No ATP at all. If you look at this picture here, you can see here that this is a sugary water solution. This is the lower concentration of sugar water here than over here. So which way is water going to move? And I'm going to contend that water always moves from an area of lower solute concentration, here in blue, to an area of higher solute concentration. So you see here this arrow demonstrating that the water molecules are actually going to move from left to right here. And you can see those guys in this middle square picture. The water molecules, there's 3 of them moving to the right versus every one that's moving to the left. It's a dynamic equilibrium situation. But understand that at the end, if it's able to, there's going to be an equal amount of water on either side of this membrane. And in addition, there will be an equal concentration of sugar water. Water is the only thing that has moved here. If you notice these big green, we'll call it a solute, which is solute is anything that's like a solid in a mixture. It's too large to go through the holes in that membrane. And if you notice, you can even count the number of solutes on one side and the other. But as a result of the water moving, now there's an equal concentration of sugar water. Meaning if you drank from one side and you drank from another, neither side would taste any more sugary than the other after the experiment has taken place. Before the experiment has taken place, if you look at the left side, there's going to be, if you tasted this sugar water, it's going to be less sugary than this sugar water over here, but that's not the case at the end. That's very important for you to understand, because we're going to do some laboratory exercises on this. If an orange dye capable of passing through the membrane was added to the left side, how would it be distributed by the end of the process? Orange dye. Imagine that this dye is able to fit through the holes in the membrane. And would the solution levels in the tube on the right be affected? The solution. Remember, solution is a solvent plus a solute. Solvent is a liquid portion, solute is a solid portion.
Diffusion is the net movement of molecules down a concentration gradient. This process allows small molecules, such as oxygen and carbon dioxide, to cross the plasma membrane. Most polar molecules, such as sugars and proteins, cannot freely cross this lipid membrane. Although water molecules are polar, they are small enough to pass through the membrane freely. This special case of diffusion that involves the movement of water molecules across a membrane is called osmosis. If a molecule, such as urea, is added to one side of a membrane, it will not be able to diffuse across the membrane because it is both large and polar. Because of its polar nature, it will interact with other polar molecules such as the water. This interaction reduces the number of free water molecules on the right-hand side. With fewer free water molecules on the right-hand side, there is now a net movement of water molecules down their concentration gradient to the side with the urea molecules. Because more water molecules are moving into this area than are leaving, the water level on the right side will rise. If the osmotic concentrations of two solutions are equal, the solutions are isotonic. However, when the solutions have unequal osmotic concentrations, the solution with the higher concentration of solutes is hypertonic, and the solution with the lower concentration of solutes is hypotonic.
Take a moment, try this question on page 141, please.
This membrane separates pure water on the left from a solution of sucrose and water on the right. The membrane is semi-permeable. Water can cross it, but sucrose is too large for the membrane's pores. Water molecules will move from a solution with a lower concentration of solutes to one with a higher concentration of solutes. A solution with fewer solutes has more water molecules that are free to move about and follow their concentration gradient across a membrane. Thus, there will be net movement of water across this membrane from left to right. This diffusion of water across a membrane is called osmosis. Osmosis is of great importance in the water balance of all cells.
So, which way would water move in this example? You have this environment that has all sorts of different oses or carbohydrates out here. This is in molarity or moles. I'm going to tell you that there's less solute in the environment than there is within the cell. So which way is water going to move by osmosis in this example? And why? Go ahead and press pause if you need to. And of course you see water moving into the bag because there's more solute in there. Water's going to go to an area of a lower water concentration. Just like the octopus example, I've got one with frog legs. This guy's something similar to a salt legs. Obviously, this is a dead frog, and it's going to cause a crazy thing to happen here. Just imagine water leaving cells as a result of now a more solute-rich area on the surface of the cells.
Wow, they are really going.
Oh, that's freaky.
Oh, man.
Helen, check this out.
Jeez. Well, we're getting it on camera for posterity. Man. That's something.